as I said, today we will talk about RPC. But towards basically the second half of the class will be anything that will not be on your second quiz. But I want to bring it out because these are important system and network topics, to be honest, things that cover both module number 1, the OS, and module number 2, because the two things are super related. Then next week, I'll start to talk about Comarch through my spinal cord, not through my brain, because I've been working on this for a long time. Then on Friday, don't forget we do have quiz number 2 on the computer network. All right. So quick recap of the system. All right. This is basically what you've seen so far from system skill. You remember the slide usually non-color version. The reason why I colored this was basically, if you think about it, right? There are elements of the system in the middle, and then there's element of like the algorithm designs, the program design, software development, software engineering topics to the top, how you fix certain problems, and then there's basically material science and electronics at the bottom. Physics, how atoms work, how material works, how do they interact. You go down all the way to electrons, right? And what we covered so far, right, is from the top part, without the compiler. That's why it's a different color, because we're not talking about the compiler. It's like a totally different like topic that requires one semester of discussion. Okay. Then we have the runtime system, which operate your network, your OS, your database, whatever you have to do to make sure your computer runs. Right. And we talk about the power abstraction quite a bit already. Why do you prefer programming Python? Okay, what's good about Python? Yeah, easy, right? I mean, think about it this way. Once you're a software programmer, let's say you're in the States, not here in Thailand. Let's say you're in the United States, you're gonna get paid like maybe $100,000 a year. That's like the equivalent of like at least 10 good computer, if not more, right? So your time worth a lot of money. Companies want to be able to make sure you can work as fast as you can. So abstraction helps, okay? You can program in Python. How many people use Rust already? How many people have the love-hate relationship with that language? Explain. Yeah, it's like you can't compile ever, right? Because the language itself poses certain restrictions that would guarantee really high performance and really nice memory protection, really nice method to control the memory. You don't have to malloc, right? How many people have the love-hate relationship with C and C++ as well? Just hate it. Okay, yeah. So you see, right? Everyone hates memory allocation. Everyone hates signals. Like sending signals to kill something. Hate it. How about handler? Handler? Network? No. Okay. Yeah. You saw from one of the demo that we do like HTTP request through Python, right? How's that? Yeah, it's nice, right? You can build an API that wrap it around, right? I mean, you don't have to implement the whole thing in Python. You call that Python function call. It actually invokes another library, right? And that library can be implemented in C++, and that works, right? So why should you care? Sorry about that. There was a slide I also used for the IoT class back in PCS as well. But why should you care for anything, any system, any IoT database system, or even things like your program? There are cases, right? How many people have like mobile app on their phone, and there are certain things that like are unexplainably slow? Sometimes, right? I'll give you one example. There's an app that I have to use because I was in a Muban, right? Owned by one of the company, which I will not say because we're recording. The app for the to do the visitor and everything is really slow. I don't know how they implement it. but definitely something is wrong with it. It's actually iPhone because I'm using iOS, right? So I also understand the problem with Android because sometimes apps can be abysmally slow when you look at your friend's phone on the same app, right? Because Android had this, I need to implement the OS, I need to implement the app that works on every single Android phone from every single manufacturer, which is not an easy problem. Not an easy problem at all, right? But you need to know the system to actually understand things like caching. This is like the second time you learn about caching. You were learning about caching in system skill, right? About how we can cache the memory into this on-chip CPU memory that is a lot faster. You can then also cache the data you request through the website on your local machine, on the local server nearby in Thailand, right? So this concept is really, really useful and it's used everywhere. There are companies that dedicate to, for example, performing caching. Do it well, I'll sell that as a product. And people actually do pay a lot of money for that, right? So here is a typical look at the kernel, right? You look at the program called like API, library, system call, right? So those are things you've learned so far, right? And then on top of it, you think about it, there are things like the file system. How do your computer actually understand the disk, right? What if the disk is network? Anyone use a network file system before or NFS? Have a shared drive? Yeah, how does it work? How does it know what hard disk to go to when I want to access the data? Right? We're not going to cover that. Again, for your quiz, it will be about RPC, but I want to motivate that. There's a lot more to system. I want to do it today because we're going to transition to hardware soon, right? Then there's the IPC, which is what we call inter-procedure calls. If I have two programs running, how can I make sure they can communicate? We can use inter-procedure calls, right? Then there's a scheduler, which you learn in module number 1. Things like first come, first serve, right? Shortest off first, those are the scheduler. Then you have the device driver, you have the dispatcher that map your task, which is now either be a multi-process or multi-threaded, or single-threaded, if you will, or single process. Works as well, right? Through the hardware. Then we will learn about the ISA and the hardware in a bit. Right? So the kernel, as you can see, right, is the primary program that is there to operate your computer, right? Now, with distributed system, can someone give me your understanding of the word distributed system? Huh? No. All right, so let's say I have an app that I want to provide as a service for a bunch of clients, right? How do I scale them horizontally? Buy more computer, right? And make sure they maybe service, like certain client go to this computer, certain client go to that computer. Another thing I can look at is like, anyone here heard about the word supercomputer? What do we use it for? Science, math, running crazy things. All right. Why do we need that? What if you do crazy math on my laptop? Yeah, something will die. Either I die first because this thing will not finish, or this thing die, or both, right? Then you need a bunch of computer. But can you have a giant monolithic CPU? Like single CPU somehow as this monolithic thing that would run? No, right? So you need a bunch of CPUs, a bunch of maybe GPU as well, right? To run your scientific job, or even things like AI or machine learning, or like things like DNA sequencing, right? When you have a bunch of those, you need to connect them together. Things become like each node has its own system, right? If you think about it, there are a bunch of computers, they would need their own OS, but you have to also connect them. You have to connect multiple machines right, together so that they run a single job in the case of supercomputers or multiple jobs. I mean, if you will, right? That's why we call it distributed system. It's a system basically that consists of multiple computing nodes. It's as simple as that. Computing nodes in this case are connected, right? And as you've done already through like this work address and all these things, work items can be distributed to each node based on some kind of schedule. It can be in the OS, it can be in the system. In the case of distributed system, I mean, if you think about it, right? What if I rely on the OS to do a job scheduler for the entire system? What will be the challenge? All right, let's say I have 4 machines. Each machine has its own OS. If I need to do job scheduler, doesn't mean I lose one CPU on the machine. Just to do job scheduling, right? That's a design trade-off, right? How do you do scheduling? Give me a second. Sorry about this. I need to take this off. Okay, let's continue. All right, so in this case, again, like your work item can be distributed to each node. And this is basically in a lot of cases, this is where complexity comes in. You're gonna have shared data. For example, right? If you look at Facebook or Instagram or TikTok, right? When you upload a video, everyone's supposed to see that. When I said everyone, it's everyone's device, their own computer. And when you modify, let's say you edit the post, right? There should be the update, not the old one. Now, how do you handle the shared data? That's the one of the challenge. When handling shared data, sometimes we can use this thing called message passing, right? Each node can also have multiple type of architecture in the system. This is where fun comes into play as well. Look at supercomputer. You have the CPU and have the GPU. Look at your data center. Sometimes these days you have the CPU, you have the network adapter, which can be used to run something. Because these days network adapter is really, really fancy for the data center. They're programmable. So people are like, hey, since they're programmable, let's program them to do something because I have them sitting around. It's not running, well, it's just managing traffic. Why can't we program them to have a really smart traffic management, right? And what you understand as the cloud, quote unquote, is basically a subset of distributed system. It can be something, even things like your 2 laptops connecting among each other and send data over back and forth, right? Now, here's the issue. How do I handle shared data, right? There's this thing called interprocedural calls. If I want to call another CPU function that is running on a different program, right? I can allow IPC to have I have 2 processes running. Process 1 want to call process 2 function. Think of it as I have client and server, but it's the same machine. Process 1, process 2, all right? Process 1, process 2. Now, what if I want to call process 2 function? It means I need some protocol, right? Because function means that I can pass data into the function. Now, if process 1 is calling process 2's function, whose data it is? Let's say I have a function called f, and the data input is x. Who owns x? Process 1 is calling f of x on process 2, so who owns this x in this case? Process 1, right? And who owns f? The function. Process 2. Process 2 is the ownership of the function call. The data is from process 1. With what we learned so far, with virtual memory and all those things, can process 2 access x? No, right? That's where IPC comes in. That's why we call it message passing. This data x is passed as a message to process 2 and they're like, hey, run this. Here's the data, right? Almost in a similar fashion as your client server connection and communication to HTTP. I tag the data in, the server got it, run something, send the data back, right? RPC, in this case, when you have two nodes, not on the same computer, things get a little bit weirder. That's why we call it RPC, remote procedure call. R stands for remote. It means that it's not my CPU even, right? I have two computers that talk to each other. The target receives the call, reply back, right? So the way you do this is simple. I send the message over, I wait. I send a message over, I wait. The target run the function call, return back the data, and that's it. This is almost like what you've seen so far with HTTP. I send the data over, server handle the data, send back to the reply. Same thing, right? Timeline is the same. This is managed by the RPC runtime. Another alternative model is what we call shared memory. Shared memory means that I would assume all these CPU that are in the same, like maybe in the same server, but two sockets. I can have a really giant motherboard that can put in like 4 CPU. Each CPU has its own local memory. And then in that case, when I connect them together, they share the memory. You can think of the same thing in the fancy server grade GPU. For example, anyone heard of A100? It's like one of the GPU used in data center, right? They also use shared memory as well when they want to manage the memory on the GPU because they're not on literally on the same node. And now, the way remote procedure calls is going to be something like this, and this is going to be used a lot in microservices. Right? I have this open-end question in the module 1. It's like, what's microservice? This is monolithic or monoliths. Microservice is when you basically want to like spawn off different services for your product and hopefully make sure that most of the communication happening inside the service itself, not across different services. But if that's the case, you better maybe use monolithic, right? Then in many cases, you can use things like RPC to communicate, or even things like RESTful API, which we will not talk about for the purpose of this class, but you probably will learn it in the, I think, scalable system. Now, you have the client and the server, okay? Something familiar, client and server. Two process running, process client and process server, two different machines. The interface will make it look as if the client called this guy managed the procedures to print up, for example, return the data back. From the programming point of view, this is that's it. It's simple. Use RPC. Internally, what happened is the client will call the client stub. This is the same as the other stub that you've seen so far. Basically, it's like unwrap this, perform the proper call using the RPC runtime library. The RPC runtime library then use the network layer to send the message over to the endpoint RPC runtime library at the server. Now, because these are network messages, I mean, it works the same way as what you've seen so far with the network protocol, right? You can determine, okay, here's the domain name of the server. Here's what I want to run. Then you figure out, okay, what's the IP? What's the physical, like what's the MAC address? I go there, okay? Then when the server got it, you go through the server stub to run. Basically, if you think about the round trip, right? If you think about the round trip, even though you just want to do this communication back and forth, right? You actually have to go all this way, down this way to run, then all this way back, right? So what's one of the possible downsides of this? How many steps do you have to perform to actually finally got your return function, your return data? Quite a bit, right? You go through the stub, you then go to the runtime library, then you go to the network, all the way to the server. I call the function, then I'm done, right? So here's the benefit. As we saw earlier, this is easy to program. Once I have the API, call this function on the server, hopefully I got the reply, right? If I don't have the reply, then some other policy to handle when the case server didn't respond. It's transparent, assuming you know some basic system programming, that's it. Your knowledge, for example, is good enough. I'll give the demo code out on Thursday. As I said, I'm basically setting it up in my lab right now. So you can call a function that just print hello world using RPC. This is another nice thing, architectural independence. What does it mean is, this is also the same HTTP, it's not dependent on the architecture. Basically, I just pass around the function call. As long as each computer has the RPC library installed, it knows what to do. I can change the CPU to the M1 chip. It should still be able to call RPC. All right. And there's one more thing. Doesn't mean it's simple. Doesn't mean it's simple, right? So with the stub and the library, right? Here, now one of the problems is we have to go through the stub, right? And how do you actually send the function call? So the thing is, the solution, you have the IDL or interface definition language. And there are many of these. But the key idea is you use this language to send out the function signature. Anything related to what function you're supposed to run. So that you know that, hey, run function at this particular line of code in the server. Now, if I have a server that can take RPC, if I have a server that I can take RPC call, I can communicate what function I want to run. Do I have the server that can provide services like maybe a database server? With this, can I have a database server, for example? I take in RPC packet, say, hey, query this particular key from this table. I can, right? I can. Then in that case, your client doesn't have to maintain the full database. It doesn't have to do anything, basically. Then, hey, this is a query I want. The server takes it. All right, here's your data. It's in this table. Here's all the attributes based on your ID that you want to query. The client side and the server side, the OS also provide the interface with the stuff, right? So that's another possible optimization point on both ends. So there are works that looks into, okay, I know that these steps that you have to do. What can I do to optimize them? Make sure the stop calling is faster. What if I want to minimize the bandwidth that I consume? Do I do compression to send the data over? I mean, these are all the things that you can do, because basically anything besides this is programming, right? If you think that there's a lot of traffic, there's a lot of data involved, maybe perform some compression so that the network is not as loaded. Then you make a trade-off, because when you receive the packet, you need to decompress, which takes more time, right? These are the typical things. Again, first of all, set up a client server connection. You've seen this already. Then you set up the actual call along with the argument by setting up the client side stuff. Setting up the client side stuff. Again, we see the demo. We built the message from the client side. Then you use the RPC to send the packet over, right? The client side handles the RPC and send the message. The server side pass the message to the server side stuff. In order to actually raise it above the stuff level so that user application can run the data. Once it runs the data and packet in the server side stuff, send it all the way back to the client. And now, when the server OS sends the result back to the client receives the packet, then unpack the whole thing. And as you can see, that's a lot of steps. Okay. That's a lot of overhead. So you don't want to blindly, that's one more caveat here. It's like, if you want to run things in the cloud, don't blindly run things in the cloud. Design it first so that you minimize this system call. Right. Now, there's multiple different style of RPC. You can do shallow integration, which means that I'll use library calls to do data formatting. I'll use library calls to access any function. This is basically what I would expect from the basic thing. I have libraries that say, hey, this function would establish the connection with the server. This function would send the data over. And this is like how you put in the function call. This is a function name. Use it. Install the library. Then look at the documentation. Use the library. Now, you can also do deep integration, which means that, hey, maybe I think I know what I'm doing. I'll build my own data formatting. I'll decline whatever type I need for my application, because maybe your application really need to optimize for a certain type, like floating point. Now, afterward, I'll use the idea. Idea is that thing that registers the function signature, right? From the other slides. I have the public functions that are registered through the idea. I'll say, hey, people can call this function. And here's the data formatting. If you want to call this function, make sure you have this format. That's a deep integration. You don't use library. You say, hey, any incoming RPC packet, do it this way. Basically, you're kind of building your own library for your special purposes. This basically would now allow the compiler and the system, compiler through your programming, system through the server OS and the host OS to perform the RPC, rather than relying on a public library or even not public library that handle the RPC for you. All right. Now, here's the fun fact. Network can go down, server can be flooded, right? So these are some of the possibilities of things that are going on. So in reality, right, you won't be able to call the function once, right? I mean, think about it this way. You call a function, but because the network can be unreliable, it means my function call never get run, right? And ideally, you need to be able to handle that. The RPC system needs to be able to handle that. So how do we implement this? What are some ideas that we learned so far, actually? Rerun, retry, right? Wait for some certain time. If I don't have the data back yet, hey, maybe something's wrong, retry. So these are some practical RPC semantics. The first one is what we call at least once. It means that the client will retry. This is what we've seen so far. I will wait for some amount of time. If I don't have the reply by that time, retry, but until I got it. The second practical implementation is what we call at most once. Now, the server is done on the server side, client send the RPC. Then it keeps the list of any active RPC ID. And then if there are any unprocessed requests, if there are any unprocessed requests, you resend them saying, hey, client, this is unprocessed. This is something weird going on. Resend. The reason why we call this at most once is the server would notify the client, say, okay, I'll just run it again. That's why we call it at most once. At least once, again, as the name suggests, I definitely need to run once, but I might have to call multiple times until I get the data, right? The first bullet point is simple. I have timestamp and then I keep retrying. The second one is a little bit more complicated, but a little bit more guarantee as well. If I have any unprocessed request because the network is down or whatever, I will notify the client because I have this list of the active RPC that still have to be handled. Now you can also do, yes. Basically on the server side, right? Basically once you have the server client connection and two sides want to communicate, client want to run a function on the server. At most once is, let's say I establish the active RPC I'll tie that particular request with an ID. But once you process it, right, you need to guarantee that the client actually got it. Otherwise, the client, I mean, if you do at least one, you can keep seeing the request from the same guy. And here's the problem. If you do at least one, there's a chance that you're going to be flooded by the client. Whenever my network is unstable, right, the client thinks that, hey, it's unstable, I'll resend. Now, let's imagine that 1,000 mobile phone doing that resend right now. It's like there's a concert opening up and you have to book the concert, right? Everyone refresh. That will flood the server even further. The server die basically. So in the case of Atmos one, basically you tell the client, hey, don't keep sending things over. Send it once, I got it. Now I need to process your request, and if there's any active requests that hasn't been processed yet, and when I reach the time, I know I'm gonna process this ID, then I notify the client. Yeah, you block. Basically, you tell the client, don't send any more requests of the same ID. I got it, but I don't know when will I have time to process. It's like when you email me with like whatever things you want to do, right? I have unprocessed requests, and then I'll reply eventually, right? In that case, you basically want to send an email over. You're like, okay, I'm not gonna send an email maybe until 5 days later. In this case, like I will not send an email ever, and I'll wait until I reply back. Open the inquiry, like it's like ticketing system. I open a ticket, then the company that got your ticket for the issue, right, will open the ticket, then notify. But you don't know when that ticket will be open. Same concept. Yes, yes, but just one for the same request. That's why we call it Atmos one, because you guarantee that that's it, right? Then you have the transactional method, which is 0 or 1. You guarantee it's a transaction. Transaction is it's the same way as how we would define transaction. I do this to completion and I'm done, or nothing happened. If I go through the middle and like something happened that are weird, I abort. I will have to retry the transaction. It's almost like at least once, but if the whole transaction is being processed on the server side, right, you would need to know the status, whether you abort or not. In this case, let's say you have to send 2 requests of the same ID. The second request, you need to make sure abort the first request somehow. If it's at least one, you don't have to abort. You can handle it differently. Maybe it's done already, so I just ignore the second request. Or if the first request hasn't even been run, maybe I just use the second request or whatever. In this case, you need to guarantee this only happen once, not twice, not 3 times. Okay, so that was a synchronous. Oh, that's the side on how many messages you have sent. The second is asynchronous RPC. But so far, even with the server client model, right, you also have to always do something this way. You send a message, run, then you reply, right? So that synchronous RPC call. And this is slow because every time you do something, you have to wait until you got a reply. You can also send this asynchronously. So basically, it's a resuming. When I have the result back, I send, I wait, then I resume. You basically build internal interrupt handler saying, hey, if I got the reply back, call this interrupt. In the meantime, I will run something else. So asynchronous call, I send a message. I send a message over. This part will invoke an interrupt. In the meantime, at this time, the CPU side on the client runs something else. It can send another message, for example. It can run a totally different process. It can keep running the same process, but send many more messages. Each message has its own interrupt handler to know, okay, once I have the data back, what function do I run? Okay. Any question about asynchronous RPC? Who would like to do this for the lab? Probably kind of way easier to make bugs, right? Because every time you have the message in, it has to call the right interrupt with that reply. Okay, so this is a lot faster. This is more practical, but you also need to make sure that it's correct. Now, more reading on gRPC if you're interested. This is basically the protocol that everyone uses right now. Okay, this library is what we would use in modern day workloads. Quite a lot, actually. It has a bunch of optimization on how do you put the data format so that it's actually if you will, right, it's more compact. So your data packet is smaller. Yeah, also the way to actually make a fast connection and send the data over quickly. Totally recommend once you're done with like your project, for example, make sure you finish your project first. All right. That's it for anything related to your exam. Again, let me go over more topics on OS and network that I think are useful. Before that, let's do a quick break. Then on Thursday, I'll do a demo on RPC. I'll extend I think that's one more. Do I upload this before? Yes, I'll upload this before the exam. I will make sure I post the code for the demo as well, because that's what I forgot, and then I realized, so we have to do it on Thursday. I'll extend the in-class exercise so that you have more time after you see the demo and you see the code for the RPC. Because once you see the code, it's much easier. Like, okay, this is how I establish connection. This is how I do the function problem. All right. Let me pause the recorder right now. Would it be surprised if I check the recording button? Like it's been recording all the time. Yeah. All right, so these are other topics in OS and network. All right. Again, if you're curious about career path, you want any advice, feel free to let us know. We would be more than happy to help you. I know that many of my feedback on career path is going to be high level, because it needs more. Like these are mentorship kind of thing. It needs time to like pick what you want to work on and optimize that. All right, let's talk a little bit about microservices, because you might see this a lot more going in the future. Somehow we call this online data intensive system, or LDI. The key idea is server can have any unpredictable load. I have a server up. Sometimes there's a news. For example, let's say there's a concert nearby in Thailand, right? The server load for news and like Ticketmaster, for example, for that particular server, will have a lot more traffic coming in. You can have things like tail latency problem. Tail latency is if you rank all the requests based on how fast they're being serviced. Tail latency is the time it takes to service the poor guy at the end. For a random request that never been serviced, how long have they been waiting? So that's what we call tail latency. You want to bring it down. You don't want any random guy to wait like 5 hours to go to Google. You want to make sure the tail latency, 99% latency is like 5 milliseconds or something along that range, right? Microservices allow things like system reliability. It also gives you the separation of the specialized function. I want to build a service just to do X. For example, like GPS service. It's just designed to do GPS. Someone can call me. I'll give the coordinate. That's it. All right. Microservice to handle like money transaction. Give me the money you want to take out of your account. I'll drain the account for you. That sounds wrong. Yeah, but you got the idea, right? And make sure it's transaction based. If something happened in the middle, I cancel the whole thing and I notify the sender. Also ease the development, because you can basically now, let's say you run a big company, one team will be responsible for this service, the other team for this service, and hopefully they do their job, right? Now you can tell, okay, this team has some bugs here, fix the bug. This team has a different bugs here, fix the bugs. And then the cross-team communication is minimized. Once you define the APIs, once you define the high-level system, and once you minimize communication between the two components, you can then have each team design their own things, right? And if you compare monolithic, right? SLO is one of the keywords that means service level agreement. Sometimes SLA, SLO, right? This is basically some kind of, if you logically think about it, the time for me to finish my request. In a monolithic system, it has a lot of components, right? There are benefits for this. There are downsides for this. Let's say you send a request over, you're going to do multiple things in there because every service is in that thing. You have to do multiple steps because you might want to do just take this request, make sure you lock them, then you process the request, put this part in the database, prepare the response, send the response back. So every service is in this particular request. So it will take more time. So one request will take more time, right? The problem is, if I have a lot of people that want to use a monolith, and when things get queued up, each of these requests takes a long time. So it is harder to do scheduling because you can't just say, hey, this thing's been running for 10 millisecond already. It's already 10 milliseconds. If you have microservices, you might have finished like 2 requests already, right? So you can do coarse-grained scheduling, but not fine-grained. So it's hard to do fine-grained scheduling. If you cannot do fine-grained scheduling and you have latency spike, there's not a lot of control that you can have. But again, monolithic seems like a bad design choice. Not always the case. Everything is about the case-by-case trade-off. Because in many cases, if you design microservice that call each other a lot, it means you have a lot of data dependency that this thing depends on this thing, this thing depends on this thing call this like 5 times. Don't do that as well. So to do microservice design, you want to minimize communication. To do monolithic design, you want to make sure the overhead is as low as possible because that's a benefit of monolith. You don't have to call another service. Everything is in the same entity, right? Another thing is you have shared memory. So instead of RPC, which you send message, we share through message passing. Share memory assume that every CPU share one single DRAM, right? So even though I said every CPU, it can be multi-socket. Multi-socket means that CPU 1 has its own memory, CPU 2 has its own memory. It just happens to be on the same machine. They can share the memory, right? Now, accessing them can take a different amount of time. That's one of the issues. Sometimes we call this non-uniform memory access. We talk about this in Fun Horror. We will talk a little more in Fun Horror, actually. Yes.
What's the difference between?
Okay. Shared memory is a concept where when you have a bunch of DRAM, the CPU, every CPU on the machine, look at the DRAM, it's all shared. Not, yeah, go ahead.
It's just that the placement of the DRAM is like the CPU.
Like for example, you have a really, really big server, right? The server can come with a motherboard that can take like 4 CPUs. You can plug in 4 CPUs. Each of these CPUs is connected to a portion of the DRAM. Now, even though you have 4 portions of the DRAM, one tied to one CPU, all CPU, like every CPU can access everywhere. But accessing your local DRAM is going to take less time than a remote DRAM. That's why we call it non-uniform memory access, because you just simply cannot build a big system where there's one single huge DRAM. It's just not feasible to build that on a motherboard. You basically become like 4 CPU, 4 cluster of DRAM, they can then talk like cross like this, right? Then you have to build the network inside your system. That's literally the network inside your system. to make sure communication is done correctly. Then, because communication has to be done correctly, shared memory can be complicated as well. What if your data is modified? If you have a shared data, four CPU share the data, CPU one modify my data, right? Fun. Think about it this way, CPU one. I'll just use P2 is a processor. Each one of them has a cache, right? This $sign means a cache. P4 modify my data, so I have to update the data. If the shared data, P1, P2, and P3 has a local version in their own cache, how do you notify, hey, update that guy? All right, so we will not talk about this in this semester. We will talk about this in the ComArch class. We call this cache coherence. How to make sure we still have a functioning system in a multi-core when they have this shared cache. Because you have to have some policy. There's a protocol to ensure everything will be done correctly. Yes. Exactly. It's all in hardware. It's built in for you when you buy a CPU, it works. And we make sure it works. Yeah. But as an architect, you have to make sure that works because you're responsible for the hardware design. These are also applicable to like cloud or HPC cluster because memories on each node are being shared. How do you share them? These are actually less realistic in things like IoT networks where you have like, unique devices. That's why in IoT they use a lot of RPC. RPC means I share the data by sending the message. Sending a message, here's my data processor. Good luck. I'll wait for that. All right. Then in microservice, you have to think about what should be the threading model, right? It's basically each microservices can share one single physical machine, right? There will be this thing called daemon that kind of monitor the service. It just kicks in, it maintains the service. It's like a part, it's like a special program designed to like maintain the service. The daemon make sure it start and stop and monitor and control the service, right? You can have a different scale in terms of scalability. You can implement everything using threading, which will be painful for sure. Don't do that. You can use SA Linux through unikernel. Also, don't do that. Most of the time, you use container. Things like Docker. You might have heard of Docker, right? Docker is basically when you want to launch like some kind of almost things like a container virtual, like things that look like a virtual machine. Each has its own isolation between each container. And in this way, you can run a service using container. So the microservice still face the same problem in any multi-threading solution. Any multi-threading will run into this problem, things like locks, things like when do I wake up my threads? How do I schedule? How do I context switch? Again, microservice would have to if you design the system for this guy, you have to design this. These are different threading models, taxonomy, synchronous versus asynchronous. You've seen this already. Basically, asynchronous means I want to run whatever independent task I'm running right now, and hopefully they don't have to synchronize. There's not a lot of communication where, hey, I'm done with this communication, someone take my data. Hopefully, there's not a lot of people waiting for that data. Everything can be run on separately. Asynchronous can be things like event-based. I have an event that happened in a program. When the event trigger, some thread takes that event, processes. So if you do it that way, you can spawn as many events, and then you have a bunch of worker thread that comes in and takes the events and process that. That's how you can implement asynchronous easily. You can, for example, here you have asynchronous URL fetch. Basically, you establish HTTP client, and then once you establish, right, I want to get the the total time to establish this synchronous connection versus asynchronous. Asynchronous, as you can see here, is Python code, by the way. There's a second def in here is the inner function that say, hey, once I have the connection, call this function. Is the handler, right? This is event based. If I have the connection, print this, do this, right? If you look at it this way, I can send a request, forget about it. Once the connection is established, do this, okay? Then the second threading model, you have the inline versus dispatch mode, RPC processing. This is a little bit too deep. So in here, the key difference is for the dispatch mode, you have the request that is in queue into whatever task queue you have established. So instead of sending a request, compute, get the reply, now I have the request into the task queue. Then you can do multi-threading by having multiple workers that takes the task. Each worker do synchronous communication. Again, it's still synchronous, but each worker thread for the client handle one task. So it's multi-threaded, but synchronous. Multi-threaded synchronous. You can also do the poll base. A poll base means that I have a thread that wait, and then yield, right? So that's block system call. A poll base means that the thread is spinning and polling for work. You have to work a thread. The client send the request over. The client send the request over to the it can be the server, it can be some services. The request gets buffer, then you have the worker thread from the server side comes in and take the request. So the multi-threading is now done on the server side of things. The worker actively go in and perform the task. The poll base usually make sure that the response time, 99% tail latency over here, lower is better. The blue line is a block base, the yellow line is poll base. If the system is not flooded, it's better. If the system is super flooded, basically nothing works. Don't do that, right? This is like, somehow we call this inflection point. Inflection point means that it's the point in which the other mechanism that used to be performing poorly now do better. So for most cases, the poll base is better. Poll base is better. You can also, this is fully asynchronous. You have the worker threads on the client side that fetch the work through the asynchronous using handler that you've seen. While you have the function handler that get called when the leave node or the server, if you will, process the request. You can basically now divide into like, do we do block based or poll based? Poll based, again, worker thread, block based, single thread. I finish one thing, I finish one thing. Then you can do synchronous or asynchronous. Then you can do inline versus dispatch. Inline versus dispatch is, do you buffer the task? All right, so that's about microservice. I'll spend the last 5 minutes on how do we handle global time. How do we do it right now? Okay. All right, each computer has their own method to synchronize, and the easiest way to synchronize across multiple machines, I look at the clock and say, right now is 11:46. Now everyone knows it's 11:46. So if I do something at 11:47 and someone else do another event at 11:48, maybe I can establish I did it first, followed by the other computer. Okay. Here's the problem. You can have skew. Let's say this clock, and you walk into another room, but that's different. It's set at a different time, right? How often does that happen? Very often, right? You can have a drift. Some clock, you have to reset every 5 years. It's just off by 5 minutes. I use that like when I was when I was young, like elementary school. My bedroom clock has to be reset. I think every month because it'll be off by 5 minutes, right? So that's drift. Skew is the skew between two clocks. Drift is when the clock is actually not accurate and keep going and further apart. Now here's a simple trick. Let's say I want to send a message in the internet. I want to have some ordering of all the messages so that I can say, hey, let's say you want a text message, right? Let's say you think about text message. What if you don't have a clock? Can you read conversation? Right? Because the time of arrival, you have nothing to tell. Hey, is this the same order that someone's sending me? Right? So you need to rely on a global clock to sort the text message, for example, right? So let's say, yes.
You use like sequence numbers.
Great question. That's logical clock. Logical clock, you use sequence number. When something happens, you increase the sequence number. And then on the recipient side, you make sure that the sequence number is sorted. That's logical clock. That's another really important topic in distributed system. So let's assume message arrive with some propagation delay because message take time through the wire, right? The sender sends message at T. The receiver set the clock. So here's a trick. I would set the clock at T plus a half of D. A half of D, why? Because my delay is D. I want to make sure the delay becomes an error of just either plus half of D or minus half of D, because I know that at least the clock is maybe in that range, right? In the real world, networks are not synchronous, so you can have arbitrary D, any number of D, and they're unreliable. So it can be way bigger sometimes, right? So one of the algorithms called Christian time sync, where you have a time server S that's set to a time source, like atomic clock or something. The process P can request time. And then the way you request time is go to the server, ask the server, hey, what's the time? Because the server time should be, because it's atomic clock, it needs to be accurate, right? Now your computer will have an error of up to round trip time over 2, the D, the factor D, right? This means that I have some error of 1 plus or minus RTT over 2, okay? Now, the problem, I have one single server that connects to atomic clock. What if S go down? So what should I do? I have 2 servers. If I have 2 servers, which one should I check? Both. But if you do both, or let's say I have 10 servers in the world, every time you set a clock, you have to send 10 requests?
Or like closest server.
Closest server to you, good idea. We're getting there. All right, so here's actually what happened. It's called Berkeley algorithm. We have one master. Everyone go to that guy. Multiple slaves. Master acts like a time demon. It's the service that say, if someone asks me the time, here is the correct time. Now, master will collect all the clock value of all the slaves. This means I can now average the error, and hopefully I get the exact time. That's good enough. Then I use RTT because I can ping slave, right? And say, hey, this server is having some delay of 30 milliseconds. So I know RTT is 30 milliseconds. I mean that the time between the slave to me is that time plus or minus 15 milliseconds, right? Then I average all the time to get the global clock. Basically, I have a bunch of computers. Everyone maintain, here's my clock. that's one leader and say, I will poll what everyone thought, and then I'll do the average. Then once I do the average, I send an adjustment to all the slaves, say, here's the current time. If the master die, one of the slaves take over as the master reboot itself, becomes a slave. Basically, they take turn. If someone dies, someone else takes over, right? Now, the network time protocol, or NTP, the way it works is, I have a hierarchy of server. Class 1 is those master slaves that is connected to atomic clock. These are super accurate. Then class 2 would get the time from the class 1 server and everyone in class 2. The more the better, right? Because when I have more, hopefully it's better approximation of what's the time. Class 3 would get the time from everywhere. Best effort, essentially. Now we use the algorithm similar to Christian's algorithm to calculate the approximated error using round trip time. Afterward, right now with our internet, we are at about 10 milliseconds in terms of the approximation. So it's good enough. It's good enough for the internet. Your concept of logical time is some program only it doesn't care about the exact time at 11:53 a.m. I just care, does this happen before this? At event A and event B, is A happen before B or B happen before A? So that's the logical time. It captures the sequence. Somehow we call this happen before relationship. Happen before relationship. This is what we need in a distributed system so that we can get the correct order of every single event in your system. If you have the happen before relationship, right, then you can get you can look at what we call Lamport clock and Lamport algorithm. That would enable the really fast and correct way to perform the ordering of events. Side note, he actually got a Turing Award from many seminal work on this array. How do I sort my events quickly, cheaply, and accurately? So here's a Lamport clock. A arrow B means A is going to happen before B. Not all events are related by this happen before. I can have independent events that have no relationship, right? Let's say C is independent of A and B. C can be run concurrently in this case C to vertical bar A and C vertical bar B. Here's the algorithm. Each process in the CPU has a local clock of Li. At process I, you increment Li, that's your sequence number. All right, Li becomes your sequence number for process I. When I want to send a message, I send M, the message itself, with my sequence number. The message itself with my sequence number. When you got the message at process J, the time of J, here's the hard part. It's easy for me to send a sequence number, but once I send a sequence number, everyone has to know that that sequence number is taken. How do I do that? Because the next event has to have the Li plus 1, essentially, right? So when you receive the message, the location, the sequence number becomes the max of Lj, and the current basic Lj is processor J sequence number. T is processor I sequence number that was sent. Whoever is greater, we use that. So that we know that the next message is the max of that plus 1. Huh?
So like at the same time, just be like, okay, now what is it? After Li is 5.
Yeah.
It all says from.
Yeah.
It should be like 5, 6, 7, 8.
So this is why this is actually the beauty of Lamport algorithm is you don't have to communicate to everyone. With this, it's enough to get the global time with the ordering. Because here's this. If I send a message to someone, it means I happened before this. If I don't send a message, should be concurrent. So it means that there must be some other messages. If they are actually dependent and have to be happened before, J should be updated. Yeah. So then you can get that to get the local ordering. For the total ordering, we just use the process ID to break ties. More information, there's this thing called Paxos, which is the paper. And that's another follow-up paper from the same guy because everyone's like, this paper is too complicated. I don't understand what's going on. There's another paper called Paxos Make Simple. Okay. These are things that you don't have to know as an undergrad, to be honest, but I feel like this is actually a cool thing that people use all the time in distributed systems. So good to know at least some reference material that this thing exists. I mean, you should know that normal wall clock exists. But now you are aware that you don't have to use that. You can use logical clock. And here's how you can look further if you will. There's also a graph consensus algorithm to kind of like find a consensus across the server when things happen in parallel all the time. That's also the visualization of graph. And if we have time, we'll come back to this. What if the network goes down? If we have time towards the end of architecture side, what if the network goes down? How do we have some resiliency, making sure that the whole system is still up and not crashing, right? That's it for the lecture today. Thank you so much. I'll see you guys on Thursday. We do a demo on RPC. All right.